The title of this presentation is Bringing Hunter's Curve into the 21st Century. And also a significant part of this presentation is going to show some of the updates to the version 2.0 of the water demand calculator, and some of the changes and reasons why we made some of the changes. The reason why we're calling this Bringing Hunter's Curve into the 21st Century is that we really haven't changed the foundation of the method that Hunter used. When you're talking about Hunter's curve, you're talking really about statistics, and you're talking about terms such as the binomial distribution. That's the method that Hunter used to create his curve. And we'll get into this a little bit and explain it to you. I want, for those who are not familiar with the water demand calculator, I do want to do an overview, a quick overview of Hunter's curve, what it is, what it means, what he attempted to accomplish with that curve, what some of the flaws are with the curve, and how we have corrected these flaws to bring it into the 21st century, meaning that making this applicable for high efficiency water conserving fixtures, as well as addressing a different type of building than what Hunter addressed, which is the single and multifamily dwelling. Actually, the calling into question Hunter's curve actually started in the 1970s, nationally and internationally, because Hunter's curve was being used internationally. And since the 1970s, there's been a plethora of papers and research that was used, but there was no solutions that was practically implemented in any code book. Probably the closest was the work that was done by Thomas Conan from the Stevens Institute of Technology. In the 80s and 90s, he was looking deeply into this problem, and he actually offered a revision of the fixture units in the National Standard Plumbing Code. So he actually had fixture units per unit, number of bathrooms per bathroom groupings. He actually initiated the groupings of plumbing fixtures in assigning a fixture unit value to that grouping. And that's it. That's all that has been done since the 1940s to modify Hunter's curve. Actually, the curve itself wasn't modified, just modifying the fixture unit values. Even still, the estimates were being overestimated, and something still more had to be done. So this is what we have done. We have taken the curve into a calculator. Instead of recreating a new curve, we created a calculator to do the statistical calculations. So this presentation will show the new features. It will give a brief overview of Hunter's curve. It will introduce the water demand calculator without getting too deeply into the statistical intricacies and the computational methods. But I do want to start by saying that the Hunter's curve that you see here on the left-hand side is actually a binomial distribution of the 99th percentile. I'll show that, and I'll show you what it means instead of trying to explain it. So what was Hunter after? Hunter wanted to take the guesswork out of estimating a building's peak demand, and he wanted to apply a scientific method that would give the designing engineer a standardizing tool that could be used for pipe sizing. So he used a theory of probability that would predict the number of busy fixtures, the fixtures that will be on at the same time, out of a total number of fixtures. And the best probable theory for this case is called the binomial distribution. And this actually is the formula, the mathematical formula to create a binomial distribution. The next slide, we're going to look at it graphically to give you a picture of what a binomial distribution looks like. So to explain this calculation, you have a given number of fixtures, any given number of fixtures, and each fixture has a probability of being on, which is the p-value, and each fixture has a probability value of being off, which is the 1 minus the probability. And then you have k. What is the chances of, say, 10 fixtures out of a given number of fixtures being on simultaneously? And that's what this outcome will give you. It'll give you the percentage. Is it 20%? Is it 50%? Is there a 60% chance that 10 will be on at the same time? This mathematical formula will tell you what that percentage and what that chance is for a number of fixtures to be on at the same time. So if you would do this as a graph, this is what a binomial distribution looks like. And it's often called the bell curve for obvious reasons. It kind of looks like a bell, but it's called a bell curve because it's symmetrical about the median, which is the high point, which is here at 20 busy fixtures is the high point. This would be called the median. The x-axis is the n value, which is the total number of fixtures, and here it's 100. In this example, it's 100 fixtures. And the y-axis is the probability distribution. So what does this show us? So if we look at the median, it shows us that this high point is the 50th percentile, which means that 50% of the distribution is on one side, 50% of the distribution is on the other side, not counting the tails. So that's what makes it a nice bell curve, and that's what makes it symmetrical, because 50% is on one side, 50 on the other side. So if you look at the 50th percentile, that says that there's going to be 20 busy fixtures on, and that there's a 50% chance that more than 20 fixtures will be on. That's what this bell curve is telling us. For Hunter, that was not a good estimate. 50% was not a confident estimate. If you design a system for 20 busy fixtures with only a 50% chance that there may be more fixtures, then you could be undersizing. So what did Hunter do? He wanted something more confident. So what he did is instead of the 50 percentile, he chose the 99th percentile. And what that means is that there is only a 1% chance, because if you go over to the y-axis, that's 1%, 0.01. There's a 1% chance that more than 30 fixtures will be on at the same time. And you see that it moves closer to zero. There's almost a 0% chance that more than 2 or 3 above 30 will be on at the same time. So this was a pretty good confident level to choose from for design purposes. So out of 100 fixtures, you would design for 30 to be on at the same time. And this is how he began to plot his points to create a curve. So for example, if you have 100 fixtures for a tank type toilet, each at 5 fixture units, which is 500 fixture units, then you would plot the point where you would design for 30 fixtures at 4 gallons per minute, 120 gallons. So you go over to the y-axis, 120 gallons per minute, boom, you would plot your point. This is the 99th percentile that we saw in the earlier graph. That's what he plotted. Well, he continued to plot points with greater number of fixtures. Instead of 100, he went to 200, 300, 400, 500, and he started plotting these 99th percentile points. and then he connected the dots with the curve. And that's how he created the Hunter's curve. So where did things go wrong? Why does this curve give too high of estimates? And today we know that Hunter's curve is faulted for giving overly conservative designs. Even though the theory of probability is sound, that produced Hunter's curve decades ago, but it's not adequate anymore. And there's a couple reasons why. What was a good estimate back in 1940s should be down here. So the curve is too high. It's overestimating. And there's two reasons. One is that today we use high efficiency fixtures with a lower flow rate. And Hunter designed for the worst case scenario. But most building types have uncongested use and not congested use. So what does congested use mean? And this is the worst case scenario that Hunter used. And congestion is basically a condition of peak demand where there would be a repeated use of fixtures during peak hour. And the result would be a high probability of fixture use during that peak hour. But such frequency is not found in a single family home. So new p-values, the frequency of fixture use, new p-values would have to be determined for residential dwelling. So that was the task that IATMO gave to a task group. And this was about 8-9 years ago now that we started this project. And the task group was to work to develop a probability model. We're still working with probability, we're still working with statistics, but to develop a probability model to predict peak demands. And that was the same thing Hunter was doing based on the number of plumbing fixtures of different kinds installed in one system. And this task became more refined to that we are going to apply this probability model for water conserving plumbing fixtures and for residential and multifamily dwellings. The reason we limited it to single family and multifamily dwellings is that we were fortunate to already have data for single and multifamily dwellings. And so this would start giving us a beta model to develop a water demand calculator. And we used Aquacraft, and Aquacraft fortunately has been collecting end use of water since the 1990s for residential dwellings, and they published their findings in the residential end use of water surveys. And this really is the foundation of our new calculator. So what kind of data did we have? Well, we had surveys from 1996 to 2011. Aquacraft worked with us and they put just thousands of data points into a Microsoft Access database for us to query and to use. There were 62 cities in 9 states, over 1,000 households, and over 11,000 home days, and over 863,000 actual events, water use events. Some of the data surveys that we used was a 2011 California single family water use efficiency study, 750 homes, a 2010 EPA standard new home study with 302 homes, a 2010 EPA high efficiency new home study with 25 homes, and a 2011 Albuquerque retrofit study with about 270 homes. So it's quite a large sampling and over a wide range geographically for us to determine representative values for fixtures in single family dwellings. So querying the database, finding those peak hours of use and waiting and gathering information, these are the values that were derived from the database. So we have 2 columns here. Well, the first column is the fixture group, and the next column are the p-values Again, the p-value is the frequency of fixture use. How often, what is the percentage of probability that that fixture will be on during peak hour use? So these are the peak values in percentages, and these are the maximum flow rate designs. And these are low flow rates because these are water conserving plumbing fixtures. And again, these flow rates and these p-values were determined from the database that we received from all these residential end use of water survey. And compare the difference with Hunter. You know, Hunter had a probability of fixture use of 6.7% for the bathtub. Residential is only 1%. 8 gallons per minute, we have a design flow rate of 5.5 gallons per minute. The toilet, huge difference. Hunter assumed a 20% probability of fixture use, and we have shown from the database that there's only a 1% probability of fixture use with 3 gallons per minute for a flush tank toilet. So right there, we are already changing the parameters that Hunter used. And a lot of these overestimating errors can be resolved just by correcting the P's and the Q's, the probabilities and the flow rates. However, the binomial model becomes skewed when the number of fixtures is very small. And that told us that one method does not fit all building size. What I mean by skewed is this. Now you saw the nice bell curve when we had 100 fixtures. What if we only had 10 fixtures? Well, look at the bell curve now. There is not a bell curve anymore. It's not symmetrical. It's skewed to the one side. And this is what I mean by using a binomial distribution. When the sampling size is too small, the bell shape is no longer symmetrical and it's skewed to one side. And the sample size is too small to determine an accurate 99th percentile. Another method was needed when the fixture count is low. So this is another fault of the Hunter method. His method is good when there's a large number of plumbing fixtures for large buildings. So there are 3 algorithms that are used in a water demand calculator, and they are applicable to the building size, to the spatial dimension of the building. And we've color coded this, and this will come into play. The colors will come into play in the next graph or in the following graph that you'll see. But there's small, what we call small buildings, medium-sized buildings, and then large buildings. And these are the 3 different methods of calculation to determine the 99th percentile that Hunter used. So we're still using the factor of safety that Hunter used, the 99th percentile. We're still using a probability distribution to find that 99th percentile. But here we use this method, and we'll get into these methods, and I'll show you the difference of these methods. I'm just introducing all 3 of them right now. This method is used when the number of fixtures is either 30 or less. The stagnation probability, which means the probability of no fixtures flowing, is very high in small building sizes. If the fixture count is larger than 30, and here we have an H, we are calling this the Hunter number, and I'll explain this in the next slide. If the Hunter number is less than 5, but the number of fixtures is greater than 30, then we use a method that's called the modified Wistort method. And again, I'll explain that. And the stagnation is moderate. It's not high, it's just this probability of stagnation is moderate. Now, if the building is very large, we use what's called the Wistort method. If the Hunter number is greater or equal to 5, and it means that there's hardly any stagnation. It is congested use during the peak hour. So we'll explain these methods and what they mean. I'm not going to get too deep into it. just for communicating, you'll understand, you'll see how these come into play. So we developed these three methods to overcome the problem of different number of fixtures and different building sizes. So let's take a look at what we mean by the Hunter number, because this is going to be a new feature in the updated calculator, and we'll show you how to use this as an indicator. So this is what we've seen this bell curve before. We talked about the median, and this is what the Hunter number is. It's just multiplying the number of fixtures by the probability of that fixture. 100 times 0.2 or 20% is 20, and that is the median. So this is different than a 99th percentile. This is basically what's called the expected value of the binomial distribution. This is a dimensionless expected value and is useful for a couple things: for determining the algorithms that the calculator is going to use, and it's also used to determine the probability of stagnation. So that's the only thing that I want to explain what this Hunter number means and how it's used in a calculator. It will determine what algorithm is going to be used, and you'll see this as we go on. And it'll also help with determining the probability of stagnation. So here's the color chart. And this is really helpful, giving you a visual of what's going on inside of the calculator. So we have the Hunter numbers here, and we see where the Hunter number is greater than 5. We're in the red zone. We're in the Wisdort method. Where the number of fixtures is 30 or less, we're in the green zone. So exhaustive enumeration is being used. And to transition between the two methods is the yellow zone, the modified Wisdort method. So these Hunter numbers do come into play as the number of fixtures increase, and the algorithms will start moving between the green, yellow, and red zones as the number of fixtures increase. So here is the previous version that some of you may be familiar with. This is the basic template of version 1.4. And what we have here is the list of plumbing fixtures that are typically found in residential and multifamily dwellings. Everything in blue are values that are fixed. You can't change any of the values in blue. However, whatever is in white are values that you can change. So obviously in column B, you would enter in the number of plumbing fixtures that are in that dwelling unit. And here you see column C is the probability of fixture use. Those cannot be changed. Those are fixed. The p-values are fixed. Now the flow rates, you will see that the flow rates are identical between columns D and E. In column E, these are the maximum recommended fixture flow rates. So the values that you change in here can be changed lower than the values in column E. If you try to put in a value higher than what's in column E, the calculator will give you a pop-up warning that you entered an incorrect value that is higher than column E, and you have to adjust it lower. This gives you the ability in the future, if these fixture values become lower, if the shower head actually is lower than 2 gallons per minute, you have a 1.5, 1.2 gallons per minute shower head, you can change this value to the actual flow rate of the fixture. So these are changeable. You can change your units to either gallons per minute, liters per minute, or liters per second. You can enter in your project name. And the output values are the number of fixtures. The 99th percentile demand flow rate will be entered here after you run your calculator, and then you have a reset button. So those were the basic features of version 1.4. Looking at version 2.0, which is available now, it's been available for download for a while from my Atmos site. Nothing has changed in the where you would enter in the values into these columns. None of this has changed from the previous version. The units that were above before have been brought down below. You can still select your GPM, LPM, LPS. You can still reset it, run your calculator, but all the outcome results now are on the right-hand side. So the total number of fixtures will be entered here. Your demand flow, your 99th percentile demand flow will be entered here. And here are the two new features, the Hunter number, which I discussed, and also the stagnation probability. And you'll see how this information is useful when we move on to the examples. This is a new feature. So if you ran a calculation and you wanted to save it, you can click on the download. It will download the result to your download box, and you can save that calculation for future reference. One of the most significant changes that we've made to the water demand calculator is this drop-down menu right here. Clicking on this drop-down menu will give you the option of either a single-family residence or a multifamily residence. When you click the multifamily resident option, two more boxes will appear. The top box, you would enter in the total number of apartments in that building, from 2 to whatever. You could put in 100 in here, 100 units, 500 unit apartments. And then the second box, you would enter in the total number of apartments in this particular calculation. So if you're only calculating one apartment unit, you would enter in the number 1. If you are sizing for a set of risers to 50 units, you would enter 50 into this number. So whatever you're calculating, the number of units that you're calculating, you would put that into the second box. What happens? What goes on with this feature? When you use this feature and you enter in a number here, as this number increases, the values in the probability of use will actually be changed. They will become less than here. Again, we ran a number of simulations, and we came to understand that as the number of apartment sizes grow, the probability of each individual fixture being on at the same time actually diminishes. It does not stay the same. So this will actually become more accurate. And we've tested this in field studies. We actually have field studies from Colorado for multi-family dwellings, apartment dwellings, where this multi-use feature, reducing the probability values, we came very, very close to the actual field measurements that were made for the peak demand. So we're very confident in what's going on here, that the method of the statistical method that we're using is sound. So this is a very significant feature, and we'll see the significance of this as we move on to these examples. So the first example, we're going to look at the large building type, the large multifamily dwellings, zone C, the red zone, where we implement the Wistort method. So we're looking at the red zone first, and then we'll work backwards. So we're in the red zone. And what is the Wistort method? So we created this bell curve. We found the number of fixtures used simultaneously in the 99th percentile. Then we had to multiply this number by the flow rate. We saw that was 120 gallons per minute for 500 fixture units. We multiplied the 100 by 5 fixture units each for 500 fixture units. You would size it for 30 at 120 gallons per minute. What the Wistort method does is provide a calculation where the result would be 120 gallons. You wouldn't have to work with the fixture units. You wouldn't have to work with the curve. This would automatically compute the 99th percentile flow rate for all these given fixtures. So what this is actually called, this is called a normal, in statistics, this is called a normal approximation to the binomial distribution. The binomial distribution is a set of points, discrete individual set of points. A normal approximation is a continuous curve connecting all the points. The genius of the Wistort method, and this is named after Bob Wistort. He actually presented this method at ASPE's convention in 1994. It just never took root in any revision, for any code revision. But this was ingenious what he did. The normal approximation basically deals with the variables of N and P. And uses what's called a z-score, which determines what percentile are you using, the 50th percentile, 75th percentile. The z-score 99 means that you're using the z-score of the 99th percentile. All of this would make sense if you took an introductory class to statistics. You would understand what a z-score is. But anyway, this is a calculation. It's a direct calculation. You could enter this into an Excel spreadsheet and you would calculate the 99th percentile flow rate. What Wistort did is add the flow rate into the normal approximation. This was never done before. And he tested this against Hunter's curve, and this actually fitted Hunter's curve very accurately. So he knew that this was an accurate method, the normal approximation, to approximate what is going on here. So we implemented this in the water demand calculator for buildings that have very large number of fixtures, because again, like I pointed out earlier, if the number of fixtures is small, like 10, and you try to use this calculation, you're going to skew the results. You're not going to get an accurate result. So this Wistort method, it only is accurate where the Hunter number is greater than 5. So putting this into the water demand calculator, we chose the multifamily dwelling and say we had 100, this is a 100 unit apartment building, and we're going to size the building supply. So we enter in all 100 units for the building supply. So we have 1,200 fixtures. Look at the Hunter number. The Hunter number is 12. Look at the probability of stagnation, 0, which means that with this number of apartments and this number of fixtures, during the peak hour of use, there's going to be no percentage of no flow. The probability of no flow is 0. So if you go to this chart that we looked at before, at 1,200 fixtures, and you have an HP number of 12, you see that you're in a red zone. So which means that if you look at this and you wonder, well, what kind of calculation did this just use? Did this use exhaustive enumeration? Did it use a Wistort method? You can look at this Hunter number and say the Wistort method was used. The normal approximation was used to calculate this outcome. And the stagnation probability is very low. And look at the difference. This calculated a a peak demand of 61.3 gallons per minute. Using the fixture unit method, it comes out with 397 gallons per minute. So you can actually decrease a 5-inch building supply to a 2-inch supply. This seems very extreme, but this validates with what we have seen in multifamily dwellings and apartment dwellings that were measured in Colorado. So the next algorithm, Zone B, the modified Wisdorf method, and we're calling this a modified Wisdorf method because we have intentionally modified the normal distribution equation to account for non-congested use of fixture. These would be mid-range residential dwellings that have increasing probability of no flow cases. In other words, the probability of no flow, again, will skew the normal approximation distribution, resulting in an underestimate of peak flow. So in this chart, we included what's called the P naught, which is the probability of zero flow. And as we see, as we saw that in the large example, the probability of no flow was 0, which means that it was a congested use. Water is going to be flowing all the time. But as the building type becomes smaller, we see that the probability of no flow becomes increasingly larger. So when you're down to a single family home, the probability that there's not going to be any water flowing at all is significantly high. And this is what Hunter did not take into account with his curve, which we have taken into an account with the water demand calculator. So how have we modified the Wisdorf equation? So again, here's the Wisdorf equation, the normal approximation that added the flow rate into the equation. What we have modified is what is marked in yellow. And you will see the P naught, the P naught, the P naught, the P naught. So this is calculating or accounting for stagnation. And this is called a zero truncated binomial distribution because we are truncating, we are removing the zero flow probabilities out of the distribution because we don't design for no flows. We are designing for peak flows during peak hours. And if you add in no flow probability, it's going to skew the model to one side and you're going to get an overestimate value, or I'm sorry, you're going to get an underestimated value. The flow rate, the peak demand flow rate is going to be too low if we account for these zero probabilities. I wanted you to notice one thing, and this is really another marvel of this modified method. Looking at these P naughts, if the probability of no flow is 0, what happens to the equation? 1 minus 0 is 1. 1 over 1 is 1. 1 plus 0 is 1. 1 minus 0 is 1. If this is 0, then this whole equation becomes 0. This whole thing reduces back to the Wisdorf method, which is what it should do. So if there's high congested use and the probability of no flow is 0, this modification reverts back to the Wisdorf method. And
Dan,
now, yes.
Dan, we have a question for you.
Okay, wow.
Okay,
the questions would come earlier.
All right, this question comes from Stephen. When you say there is stagnation or no water flow, what exactly does that mean? Not enough water to serve the fixtures?
No, what it means is, take a single family residence, for example. So you have a peak hour. Say for example, from 7 to 8 in the morning, you have a peak hour. What goes on in that house the rest of the time? There is a large probability of zero flows. No one's using the fixtures, or very rarely, if someone is home, very rarely using the fixture. So when I say stagnation, I mean that that fixture is not in use. It is off. It is not being used. Does that answer your question, Steve?
Okay, well, I don't see a response from Steve, but I do have another question for you from Jaime. If Hunter's curve is updated, what is the counter effect on the flow rate on the drainage portion of the systems, and how would that affect the drainage portion of the system from the premise piping system to public sanitary system or to the treatment plant?
That's an excellent question. Obviously, we know that if you have water conserving fixtures on the water supply side, the discharge is also going to be reduced compared to Hunter's Day as well. So this does not address the drainage side of the equation, so to speak. This is only addressing the water supply demand, but that is a whole nother animal to try to resolve. And in fact, it has been discussed, and but we have not moved in that direction yet. So this same sort of thing can be done with drainage fixture units. Instead of using fixture units on a drainage side, you can calculate the actual flow rate, the probable flow rate in a drain line. The tricky part is, and this will kind of run us down a rabbit hole, the difference between the drainage and the water is that the water is always under pressure. The water supply is always under pressure, so any fixture anywhere in that system will affect the system as a whole. On a drainage side, the drainage is not pressurized like that, so you have discharges into the drain, and the only significant impact is where these discharges start overlapping each other and building up in a drain. And the drain size has to account for these overlapping discharges. If drains never overlapped, you could size a toilet for its 1.28 gallons discharge. But that's the tricky part on the drainage side that would have to be taken into an account. But that'll chase us down a rabbit hole from what we're doing here. But that is a good question. That is a problem to be resolved for sure. Okay, moving on. So for zone B.
Okay, I have one more question for you, Dan.
Okay.
Is there a data sheet entry for fire sprinkler systems?
No, this does not. This calculator is only applicable for plumbing fixtures and appliance in single and multifamily dwellings. It does not account for, because there really isn't a peak load, a probable peak load for a fire distribution system until there's a fire. And then it's more of a continuous flow. It's not a probable flow. So we're not dealing with fire systems in the water demand calculator.
Okay, one more. So how do we size a combination system to assure water when needed?
Well, you would have to size the fire suppression system independently from the domestic water supply for the building. Whether it's a separate system or even a combined system, again, you would have to add, if it's a combined system, you would have to add the demand of the sprinkler system to the estimate calculated by the calculator. So for example, this example that we have on screen right now, for the plumbing fixtures, the calculated flow rate is 16.3 gallons per minute. You would have to add to that the demand required by the sprinkler system in a combined system.
Okay, Then do we have an oversized system on the domestic side?
That's the potential. Just as much as there's a potential, if you add in a whirlpool in a residential home that has a tub filler filling at 15 gallons per minute. Obviously, that's going to be your dominant fixture. It may not be used as often, but you would have to size the supply pipe to provide that 15 gallons per minute tub filler. So when you have things like that added to the system, you do have the potential of oversizing the pipe. That's why we do not have a whirlpool as a fixture in the water demand calculator, because it is not a water conserving fixture. It would be a flow rate that would have to be added, and it would increase the pipe size just by the required demand of that fixture. And the same thing with a fire sprinkler system, depending on how many heads are required for that combination system, you would have to provide. Actually, I think if I remember, I think you would have to size it for 2 heads, if I'm not mistaken. In a single family dwelling in a combined system, you wouldn't size it for every sprinkler head. I think it's for 2 heads that you would have to size, but you would have to add that demand to the estimated demand from the water demand calculator.
Okay, that's it. That's all we have for right now.
Okay.
Thank you, Dan.
Moving on, this is zone B. This is for a 6-unit dwelling, and you're sizing again for the building supply, just for example's sake. So you put in 6, the number 6 here, and we have a total of 84 fixtures. The Hunter number is 1.4, and look at the stagnation probability, 24%. So there's a 24% of stagnation probability for this moderate size dwelling. And looking at, again, this chart, the number of fixtures is 84. The Hunter number is 1.4, clearly brings us into the yellow zone. So you know that the modified Wistort method is being used. And in this example, with 84 fixtures, the fixture unit method in the UPC gives 57 gallons per minute. The water demand calculator is resulting in 16.3 gallons per minute, allowing a reduction in the building supply from 2 inch to 1 inch. And again, this is just indicating that we are resolving the overestimating with the use of the Hunter's curve. So now we're down to zone A. We are down to the smaller building, a single family dwelling with a small number of plumbing fixtures. We are in the green zone, and this uses exhaustive enumeration. Now, exhaustive enumeration works as a macro in the Excel spreadsheet. It actually will run iterations depending on the number of fixtures. So for example, if you only had 1 fixture, there's only 2 cases. Either that fixture is on or it is off. If you have 2 fixtures, now you have 4 cases. Either both fixtures are off or both fixtures are on, or this one fixture is off and this one is on, or this one is on and this one is off. So you have 4 cases. If you have 3 fixtures, now you have 8 cases. So each time you add a fixture, it grows exponentially 2 to the nth power. So this for 3 fixtures would be 2 to the 3rd power, would be 8 cases. So a typical home has 12 indoor fixtures, 2 to the 12th power. This macro will run 4,096 cases in order to find that 99th percentile. And that's what this exhaustive enumeration does. So sometimes when you click on it, you have to wait a little while. the calculator is running this macro. Especially as these number of cases increase, it may take a little while for that macro to run. And is the reason why we limited it to 30 fixtures. Otherwise, the macro would just take too long. The user would think something's wrong with this. This is taking forever. I don't want to use this. So we limited it to 30 fixtures. And that was the reason why we limited it to 30 fixtures, to let Excel run the macro in a timely fashion to get you the result. So
Dan?
Yes.
Okay, we have another question here from Brad. Are max velocities incorporated in the pipe sizing?
Max velocities are used in the pipe sizing. It's not used to estimate a peak demand. The peak demand is your starting point for pipe sizing. You can't go anywhere unless you know what kind of demand you're estimating for. Once you know what your demand is, what your estimate demand is, then you can use all the standard methods of pipe sizing, friction losses, entering in your friction losses, going to the charts in Appendix A, knowing now your flow rate, using the velocity diagonals to give you what the pipe size is. This is only one. This is the beginning piece for pipe sizing. It's not the total thing. All this does is what Hunter's curve provides for you. Hunter curve only provides for you the demand estimate to start you off with your pipe sizing. The water demand calculator replaces Hunter's curve, but it serves to do the same thing. It provides with you the peak demand estimate that you need to use to start your pipe sizing. So going back to this, was there another question?
Yeah, we have one right here from Mark. Does the demand calculator discriminate between cold water only and cold/hot fixtures?
No. You can use the water demand calculator to size only the cold supply, and then you could use it to estimate the demand for the hot supply. So if you want to know what the pipe size should be, or what the demand is coming out of the water heater, what the peak demand required for the water heater, you could enter in all the number of fixtures that would use hot water. So obviously you would exclude the water closet. So any fixture that uses hot water, you would enter in here and run your calculator, and that will give you your estimated demand, peak demand for the water heater. That would help you in your pipe sizing for the water heater.
Okay, thanks.
So for a single family home, has a number of 12 fixtures, we see that the stagnation probability is 74%, so that there's a high probability of no flow in a single family home. The Hunter number is 3.30. And so we can go to our chart and see at 12 fixtures where the Hunter number is 0.3, lands us into the green zone. So we know that in this case, exhaustive enumeration is being used. The calculator calculates 11 gallons per minute. For 12 fixtures, the UPC using the fixture unit method gives 18.2 gallons per minute, allowing a reduction of the building supply from 1 inch to 3/4. Now, obviously, as the building, has been shown, as the building size and the number of fixtures increase, the significant difference increases as well between the fixture unit method and using the calculator. There's larger pipe size reductions. There's a larger reduction in demand estimates, which is what we would expect as the number of fixtures increase. So this is just an overall view from that the calculator, one size does not fit all. It uses 3 different algorithms. to make it applicable from one fixture to many fixtures, a single family home to a multifamily building. We see a very small hunter number as the number of fixtures becomes less. We see a very large hunter number as the number of fixtures increase. Same thing with the stagnation. Almost certain where the number of fixtures are few. In larger buildings, almost never. So a single fixture will have a big influence where the number of fixtures is small, but where you have a large number of fixtures, adding another single fixture will not have any significant influence overall. So this is the version 2.0. It can be downloaded at this link from IATMO website. And if there are any further questions.
Yeah, we have another question for you.
Mm-hmm.
This comes from Eric. How would you recommend irrigation systems be accounted for? Excuse me.
Same thing as any continuous flow. What I did not do in this presentation, I just wanted to focus on the features and the algorithms behind the features and how to interpret these new features of the calculator. What we did not get into is the provisions in Appendix M in the UPC on what is required in using the water demand calculator. So one of the provisions has to do with continuous flow, such as hose bibs, irrigation systems, cooling towers. Well, not cooling towers. You're not going to use cooling towers in a residential home, but maybe in your larger ones. But those are called continuous flows, and those demands are to be added to the estimated demand you get from your calculator. An irrigation system would be considered an outdoor demand. The water demand calculator just focuses on indoor plumbing fixtures and appliances to estimate those probable demands. So when the calculator gives those demands, then you would take the demand of the irrigation system, add it to that demand for the building supply. And the same thing for the hose bib. If the building has a hose bib, you would enter that flow rate to the estimated demand from the calculator.
Okay, we have another question for you from Randy Lorge. Dan, while we hope that we never experience another pandemic in our lifetimes, do you think the adjusted curves used in the water calculator may undersize the systems too much during these times when more people are staying home from work and school?
Well, that was another significant issue that we discussed when we queried that AquaCraft database. So one of the things we did is we compared weekday plumbing fixture use compared to weekend plumbing fixture use. And there were some fixtures or appliances that were used more heavily during the weekend than during the weekday. For example, your washing machine. So we chose as a probability factor, always as a factor of safety, always the highest probability of use. If the probability of use was highest during the weekend when everyone was at home, then we chose that highest probability as a factor of safety, rather than using the lower probability during the weekday use. So, and if there was vacations, vacation days where, I'm talking about the AquaCraft data now, if there were vacation days, those were not included because no one was home and no one was using any water. So if there were any vacation days, those were omitted from the database. So we were really targeting the heaviest usage time in residential dwellings, even the probability of everyone being at home to account for those probabilities to be effective. So even during a pandemic, if more people are staying at home, we are still addressing that peak hour. And we wouldn't have a concern over it being underestimated.